Okay, so I'm recording here, and today is June 2nd. So let's take a look at the syllabus. I reorganized the syllabus so you can look at it better, right? Okay, go. Week number. Now I put those two separate columns here. One documents the number of the week number, and the other documents the meeting number. Okay, let me do better here. Let's see. Yeah. And what you're going to do, there's one more thing that I want. We are right, here you go. Here, Wednesday was the last meeting, right? I want to boldface it. We covered the last chapter of the last section of special relativity, and we did the lab number 7, that was the flashlight bulb. And I decided, since we ended up with one additional class meeting, that one more than I was predicting, okay, I added this section, this chapter, wave optics, which is the chapter before special relativity. It's an important chapter, okay? And then we are going to have our lab meeting, last lab meeting and last meeting, right, of the semester. And if we have time, we'll review for the final, do a quick review with you. And then finally, a week from now, we have the final exam. Okay. So that's the plan right now. Let me check one more thing here. Let me stop sharing this screen. It just occurred to me. Uh-oh. Okay, I'll fix that. Okay, so let's go back here to sharing the screen. Okay, right here. And so let's cover this one right now. This one is a fun part. It requires knowledge of waves, something that we cover in Physics 7. In the previous course. And let's do it, right? Notes, please. I'm going to review quickly what we did in the topic of Physics 7 of waves. Waves topic of Physics 7, okay? And I'm going to need my, here goes this one right here. Okay. So just remember what we learned about waves, right? We have what you have right here is a pulse, the pulsed wave, but we also have waves, a train of waves, just like one of those that you see right here. This is a very important type of wave, the sine wave, but there are several types of waves, right? Let's write that down here. There are several types of waves. Physics notes. Oh, let's see. 20. Interesting. Okay, so I gotta get waves right in here. Physics 07 notes 2025. You know when our grades due? The grades are due. I believe I saw just recently. It's 10 days from the date of our final. I need to double check that. I believe is that it doesn't make any sense. 10 days should be the 19th, but I'm not sure. Okay, they usually give us 1 week. Okay, Valerie, they usually give, but I'm just recalling from memory. Okay, I believe it should be due the 20th or the 22nd. I gotta check my email. I saw an email today, and it looks like they told us that we should be on the 19th. But I'm suspicious about this deadline here because they usually give us 1 week, right? 1 week from the last day of the finals, which would be the 20 or even the 22. Okay, that's what I recall from memory. Just get back to me at the end of the class. Okay, and I will check again the email that they sent me. 14th of June. Wow, 14th of June. I see. Okay. Yeah, there. Okay, I'll do my best to finish it your grades as soon as possible. Okay, so here you go. This is I'm gonna put I'm gonna insert a page break right in here. Today is June 2nd, 25. Okay, and okay, we are adding one more chapter to the course, chapter 27. Okay, we are going to cover at least the following sections: 27.1 and principle of linear superposition, this one here. Principle of linear superposition. 27.2, which is Young's double slit experiment. It's a classical experiment, a very important one. Young double slit experiment. 27.3. Let's start with those three. And if we have time, we cover more than that. And then we do thin film interference, 27.3. I'm not sure if we're going to have time to do the others, okay? Thin film interference. For now, 27.4, 27.5, 27.6, 7 and 8. 27, 27.8, we're skipping for now. Michelson interferometer. Remember that guy that won the Nobel Prize? He was the first American to win the Nobel Prize. Michelson interferometer. A very important device, by the way. We do experiments with that in Physics 38 skip. But unfortunately, we're going to skip for now. If we have time, we cover it. If we don't, resolving power. Skip resolving power as an optical instrument. The diffraction grating. And one more, X-ray diffraction. X-ray diffraction. Okay, those 1, 2, 3, 4, 5. Let us stick with those 3 for now. Skipping for now. And the principle of linear superposition, right, was studied during our chapter of waves. And I'm going to review it. And I'm going to review it here very quickly, okay? So here we go. Let's see. I'm going to illustrate one wave, okay? This wave that you see here is called a linear wave. Why is that a linear wave? It's a linear wave because y versus x behaves linearly, but it doesn't extend to infinity, right? Extend up to a certain point. That should also be called a triangular wave, okay? And we have waves that propagate as time goes by, okay? And I'm going to show you this linear wave propagating from the left to the right. Watch out. Watch what I'm going to do. Here you go. This linear wave is propagating from the left to the right, right? And now I'm going to revert its direction of motion from the right to the left, right? From the right to the left. Here we have another type of wave that can be, here you go, propagate from the left to the right or from the right to the left. This pulse can be moving. It can be moving either from the left to the right or from the right to the left. Okay. And let me get let's see if I have a simulation here to show you. Today might be my favorite day of carrying trial, and I think that it's like as we go to. I have those things here. Let's see. Let's start with t equal to 0. Okay. Let's see if I can get. Looks like this. Let's try it again. Watch for this wave, right? Let's go in step of 0.5 seconds. This one is moving to the left. Let's see. Yeah, this one is moving to the left. It's a backward propagating wave. Let me make it a forward propagating wave instead. All I have to do to simulate a forward propagating wave is to add a negative sign in here. See this negative sign here is the one that dictates which direction the wave propagates, either to the right or to the left. Because I had a plus sign here, this wave was propagating to the right, to the left. Backward propagating wave. Backward propagating wave has a positive sign. Forward propagating wave has a negative sign. And let me write that down, the equation for this wave in case that you want to simulate that at home, okay? Principal linear superposition. But first, let us review, right? The topic of waves, okay? there are all sorts of waves. We have pulses that move from one place to another. We have triangular waves, square waves, and the most important of all, sinusoidal waves, sinusoidal waves. Okay, many waves out there, can be described in terms of a linear superposition of sine waves. Okay, that's why it is the not many, I would say all waves out there. Okay, all waves out there can be described in terms of a linear superposition of sine waves, sine or cosine waves. Okay, of all, most important of all, sinusoidal, and cosinusoidal waves. Always out there can be described in terms of a linear superposition of sine slash cosine waves. Okay? And let me remind you how they are expressed mathematically, right? Sinusoidal waves are expressed one-dimensional sinusoidal waves, okay? The easiest of all is one dimension is going to be written down. Y is going to be written down in terms of an amplitude of the wave, the sine function, okay, 2 pi over lambda. Lambda is the wavelength of the wave. And then we have another term here, okay, which is going to be x, can be either plus or minus vt. Can you remember that? Okay. And sometimes we also have a phase. Sometimes we also have a phase here for the wave. Something like that. Okay. Can you remember that? See, x plus vt, right? X plus or minus vt. This argument must be dimensionless. And phi is dimensionless because it's expressed in terms of radians, and radians is a unitless unit. Okay, is a unitless unit. So everything here inside is dimensionless. You cannot have the sign of something of a meter, 3 meters. There's no such a thing, sign of 3 meters, sign of 3 seconds. There's no such a thing. Okay, what there is a sign of a unitless number, a unitless parameter. Okay, so when we divide x by lambda, we do get a dimensionless quantity. When we divide vt by lambda, we also get a unitless unit, right? This term here has the same unit as this term here. Vt is meters per second times second, okay? So that's how we describe waves, okay? Here, this one here is a forward propagating wave. Here you go. Forward propagating wave. And then we have, like I said before, we have the backward propagating wave, backward propagating waves. All you have to do is to change the sign, okay? Here's the speed of the wave, okay? The speed of the wave. We don't need that. So that's what I expressed that in that equation, okay? I put an amplitude for the wave, and I created a sine wave that propagates in the forward direction. If I go to my Excel, we have here, see, 2 pi divided by lambda, right? E2 is lambda. I made my wave wavelength, the wavelength of my wave, I made it 20 meters right in here. And multiply it by B2, the position, X of the wave. F is V, the velocity, the speed, here you go, in meters per second. And G is the time interval, okay? Is the time, the instant of time, not the time interval, but the instant of time. This wave right now is frozen in time, okay? This wave right now is frozen in time. And let's put a time t equal to 0, right? And let's see if we can animate this wave now. 0.5, every 0.5 seconds. Yeah, see, it's propagating in the forward direction, right? 1.5. And watch out those 2 points that I have here. Watch out, those are one of the points of my wave. Like a string, for instance, right? A string, you get one end of the string and keep on moving it up and down. A wave is generated by a vibration. So that's how we generate a sinusoidal wave, by moving a string up and down. Okay, so here you go. Next one, 2 seconds, 2.5 seconds. I want you to pay attention to this point. This point is not moving. This is the point of our wave. Okay, like the string, a point along the string. Notice that this point, those 2 points, they're not moving from the left to the right. No, they're just oscillating back and forth. Okay, they're just oscillating up and down, not back and forth, but up and down. Next, 3, 3.5, 4, 4.5, 5, 5.5. Let's get as far as I can, like a 6, 6.5, and then I'm going to animate that for you. 7, 7.5. Okay, let's stop in 8. Let's see, and then I'm going to undo. The wave is going to propagate backwards because I am reverting time, right? And look at those 2 big points, right? Those 2 big points are oscillating. Here you go. What happened here? Okay, good. Now we are back to instant of time 0. I'm going to set the clock running and look what happens to my wave. It gives you the illusion that this wave is moving from the left to the right, when in reality, the points in my string are just oscillating back. Oh, what happened here? Okay. Yeah, good. Let's go back again. Here you go. My wave propagating the backward direction. Let me, make my wave move forward again, right? The distance from peak to peak is the wavelength, right? The distance from the point of equilibrium to the highest point is the amplitude of the wave, okay? Okay, so just to remind you of what you saw in waves, okay? Now, going back to my notes. You may have interference interference between two waves. What is interference? Whenever two waves collide or superimpose between each other, superimpose between each other, we have interference we have the phenomenon of interference. We have the phenomenon of interference. Okay, let me give you an example. We have the two simplest types of interference are okay. Let's put it in a different way. We have constructive interference and destructive interference. Okay? Constructive interference is when the amplitude of the two colliding waves add up. Okay? This now destructive interference. Okay, you already know what does it mean, right? If constructive interference is whenever the amplitude of two waves add up, destructive interference is whenever the amplitude of the two colliding waves subtract. Okay, I'm gonna give you an example of constructive and destructive interference right in here. Here's an example of constructive interference. We have one wave colliding with another wave. Okay, you can see that they are in phase. Their peaks coincide with each other. When the peaks coincide with each other, we say that they are in phase. Okay, and then what happens to the final wave? They add up in amplitude. This amplitude ends up being twice as much as the amplitude of the other two. Okay. And then we have the destructive interference. Okay, remember we were just reviewing the stuff, right? And here you go. We have one wave at the top at a given instant of time, and we have another wave at the bottom. They are out of phase. They are out of phase by 180 degrees. That's what we say. Okay? Here, they are in phase. Now they are in phase. The phase between them is equal to the difference of phase between them is 0 degrees. Whenever the wave is completely out of phase, the two waves are completely out of phase, we say that their phase difference is 180 degrees. When we have something like that, you do not have any wave, any resulting wave whatsoever, just a straight line, okay? Just a straight line. And then you have everything else in between. We have everything else in between. I have a simulation here, interference, okay? Right now, here you go. Let's see how I'm going to do that for you. Okay, here we have wave. I have two waves. Wave number one, wave number two. And I'm going to sum up those two waves to see what happens to the resulting wave, right? So let me just plot those two waves separately in separate graphs so you can understand better, right? At a given instant of time, we need to review that so you can understand the optical waves. Here you go. That's my wave number one. And I'm going to plot now my wave number two. Wave number two is slightly offset from the first one. Here you go. That's the second wave. Y2, Y1, right? See, they're slightly offset. They have the same wavelengths. They have the same speed. Okay. And here I'm illustrating those two waves. The difference in phase is given right in here. Okay. When they are exactly in phase, okay, wave 1 is in phase with wave 2. Okay. And here you go. Here we have the two waves superimposed because they have exactly the same phase. One is coinciding with the other. If I put just a slight difference in the phase of those two waves, here you go. You're going to see that? You're going to see that they're just a little bit offset, right? If I go back to a phase difference of 0, then you cannot see the second wave because one is on the top of the other one. But in reality, we have two waves plotted here, okay? So whenever those two waves are in phase, okay, we get an interference. We get this interference that you see here. The amplitude of the two waves are the double, right? See the amplitude 2 here, here the amplitude 1, 1 plus 1 is 2, right? If the phase difference is pi or 180 degrees, we have destructive interference right in here, okay? Let's see, pi, an angle of pi, okay? And now we can start simulating any interference, anything between 0 degrees and 180 degrees, okay? So let's go back to 0 degrees. Let me see one thing here, okay. Phase, okay, phase 0. Now I'm going to pi, I'm going to start with pi over 10, okay? So look here. Those two waves are slightly offset from each other. And then we have the resulting wave. When we sum those two waves, it's almost twice the amplitude of the other two, right? Almost twice. It's not exactly twice, but it's almost twice. You can see right here in my numbers, the amplitude instead of being exactly 2 is around 1.97. Okay, 1.97 because there is a slight dephasing between those two waves. Now, if we increase the amount of phase, let's see, pi divided by 8 now. Okay, now the wave moved a little bit, right? Do you see that? I'm going to revert it back. Here you go. See that? There's a small difference. The wave that's moving is this one right in here because this one I'm not changing at all. Undo, right? Redo it, redo it. So, I'm going to go step by step here so you can play a movie very soon. Here you go. This wave moved a little bit, right? And then what happens? We have this phase difference that's generating a resulting wave with slightly smaller amplitude. Okay? Divide by 6. Let's go divided by 4 now. Okay? Divided by 4. You saw what happens, right? Let's go back. Here you go. Between divide by 6 and divided by 4. Divide by 6, divide by 4. Do you see that the resulting wave here is decreasing in amplitude? It started at 2 and little by little, its peak is decreasing because those two waves are becoming phased out with respect to each other. We can go another one. Now we're going to have a 90-degree phase difference between those two waves, okay? Here you go, 90-degree phase difference. What 90-degree means? Means that whenever this peak is a disposition for this wave, okay, or even better, whenever the first wave has a maximum amplitude, at the same instant of time, the second wave is going to have an amplitude of 0, okay? An amplitude here, amplitude of 0 of this blue plot coincides with the peak of the other one. And note, see what happens to the amplitude of the resulting wave, one plus the other, right? Now the amplitude is 1.5 now. It's no longer 2. Let's go for the next one. 2, I'm going to put 1.8 now until I get to pi. Okay, here you go. Now it decreases even more. Okay, it decreases even more. Is less than 1.5, the amplitude. Let's go back. Now let's go back to what we had before. Okay, note, see that in this case, in this plot here, the Excel changed the scale. Okay, at this point, okay, before we had this almost 1.5, now we can see clearly that the amplitude of this green wave is definitely less than 1.5. So we are getting this, the difference in phase. What happens, right? When the difference in phase keep on changing slightly. Let's see, 1.7 now. Here you go. Decrease a little bit more, right? The resulting wave, 1.6. Let's go, 1.6. Watch out for this wave here, right? And also watch out for the difference in phase between the red and the blue one. Now we're going to go for 1.6. Okay, 1.5. The resulting wave, the resulting sum of the two waves results in an amplitude that keep on decreasing. Okay, now 1.4. Here you go. Do you see that the green wave is, amplitude of the green wave is changing, is decreasing little by little, right? Look here now. What was an amplitude that was twice initially, now we have an amplitude that's less than 1, because those two original waves are becoming phased out from each other. We're reaching almost 180 degrees phase difference. Okay, almost 180 is 180 divided by 1.2 right now. You go. What now? We're gonna go for a 1.1. Okay, the wave is flattening. See that? Until it becomes, I'm gonna go 1.05 divided by 1.05. Let's see what we get. You go, becoming flatter and flatter, right? 1.02, and down the next one is just pi divided by 1. Okay, now you can see clearly that the blue wave is completely off phase with respect to the red one. And because they're completely off phase with respect to the red one, when we sum up their amplitudes, the resulting wave is completely flat, has an amplitude of 0. Okay, so that's one extreme, right? And you're going to see the other extreme. The other extreme is the one that you have complete full constructive interference, right? Here you go. Constructive interference with amplitude equal to 2. And again, little by little, I'm going to change the phase so you can appreciate what happens when the two waves are phased out. Okay, here you go. Little by little, the amplitude of the green wave becomes smaller and smaller. Okay, here you go, smaller and smaller until we have a complete destructive interference. Okay, I'm going to do something else too to give you an even better illusion of what is happening. Okay, I'm going to plot I'm doing there's a reason why I'm gonna do that. Okay, let's see. I have a total of 500 points. So from 0 to 250, I'm going to set up, I'm going to plot the value of 2. From 251 to 500, I'm going to plot the value of minus 2. Why am I doing that? I'm doing that just to freeze the scale of my waves here, okay? That's why. And now let's start all over again. And now what I'm going to do now, I'm going to erase all those graphs that you see here. Hopefully you're already familiar with what I did, right? I'm going to erase all the graphs that I did here. And I'm going to plot all of them into a single graph. Here you go. The first wave is the blue wave, right? The second wave is the red wave. This other wave that you see right in here is the first wave plus the second wave. And here, I'm putting this one here just as a placeholder to make sure that this scale here is not changed when I'm doing the simulation, okay? And I'm going to go with the phase. I'm going to change the phase all over again, okay? Just like I did before. 0, phase 0, okay? Here you go. Wave 1 plus wave 2 is this one right in here. Violet color, right? And now I'm just going to repeat what I did before. Pi divided by 10. Pi divided by 9. The waves are coming out of phase. Pi divided by 8. Pi divided by 7. Divided by 6, right? Divided by 5. And now you're going to see we are not going to have that jump, that big jump that we saw, because I'm freezing this scale. Divide by 4, divide by 3, divide by 2. Okay, and now I'm going to go 1.9, 1.8. I'm doing that so you can play a movie, right? And you can see how this whole thing evolves as time goes by. 1.5. Let's go 1.3 now. 1.2. And the resulting wave is becoming flatter and flatter, right? We can 1.1 divided by 1.09 divided by 1.07 divided by 1.05 divided by 1.03 divided by 1.01 divided by 1.00. Okay, and now we are going to revert the time. Okay, here we go. And start from phase difference equal to 0. Okay, so here you go. Full interference, full constructive interference, and on the other way, and at the very end, full destructive interference, right? So here you go, little by little, we see that the amplitude of the resulting interference decreases until you have full destructive interference. Okay? So that's what you have to understand. And we need this type of information to understand what's going to come next. To understand what's going to come next. Okay? So let's write that down here in my notes. We may have interference between, we have, we have full constructive interference. When the amplitude of the resulting wave is the sum, is the separate sum, right? Sum of the amplitudes of the other two waves. And then we have full destructive interference. Full destructive interference. Whenever the amplitude of the resulting wave is 0. Okay? In the first case, we say that the wave, the two waves, right? The two waves are in phase or in synchrony, right? In synchrony. Are in phase, i.e., their phase difference is 0. In the second case, we say that the two waves are out of phase, are completely out of phase, or completely out of synchrony. In other words, their phase difference is 180 degrees or pi. Okay? Then you have everything else in between. Then we have everything else in between, right? Then we have interferences that fit everything else in between. Okay. Now that we got this idea, we can proceed. What time is that? 10:30. We can go another 10, 15 minutes, right? Wave optics. So here you go. Here's a simulation of a linear wave. And you also saw a simulation of a sinusoidal wave. What else do we have to know about that, right? Remember, we're reviewing that. We have to know about reflection of waves as well. Okay? There are 4 types of reflection. The first one is a reflection of the fixed end. A wave colliding against a wall. Okay, so here you go. Here's the wall. One end of the wave is right in here. The other end is right here fixed. It's not moving up nor down. This one here, they can move up and down. So we have to move up and down in order to create this wave, this pulse of a wave, right? So this wave is propagating from the left to the right. Okay, the forward propagating wave. As time goes by, the wave moves forward until it reaches the fixed end. What happens at the fixed end? Something interesting happens at the fixed end. Because this end is fixed, you know, it will always have an amplitude. This point will always have an amplitude equal to 0 because it's fixed. And it will generate an interesting wave. The wave will reflect upside down, okay? Because this point here must be fixed, the wave will be reflected upside down, okay? And then it moves back to the other end, right where it starts. So here you go. Let me write down in my notes. We also have reflections, wave reflection, wave reflection. There are 4 important types of reflection. Okay. 1, reflection from a fixed end. Okay. Reflection from a, let's see how I wrote that down, from a free end. Let me get rid of those slides, otherwise it becomes too much for me. Let's see, this one. Okay, good. Now I turn off everything from a free end. Then you have a reflection from the interface between 2 media. Okay, one media is from a heavier medium to a lighter one. Okay, from a lighter medium to a heavier one. Okay, medium. Monte Star. Okay, so 4 different types of reflect. You're going to see what I mean. And this and this has very important consequences when we deal with wave optics. Okay, the first case, is related to reflection of light waves, like reflection of a light wave from a 100% reflecting mirror. Okay. Here we do not have a no parallel in wave optics. Here, wave moving towards the interface wave. Let's see, light optical wave, light. Let's see, light wave moving inside a medium of higher refractive index towards the interface, towards a medium of lower refractive index. Okay. And then this other one is just the opposite. Light moving inside a medium of lower. See, that's what lower and high refractive index is all about, of higher. Okay. Let's see what happens when something like that happens. When when we have this type of circumstances, right? So, okay, reflection from a fixed end. Okay. Phase reflected wave has a phase shift of 180 degrees. Okay. That's what you saw before, right? Here you go. It was upward. The wave was initially upright. After the reflection, it becomes downward, inverted. That's what we call a 180-degree phase shift. Okay. Then what about if you have a loose end, a free end? Okay. In a okay. I gotta. Here you go. Better now. The orders were incorrect. Free end. The wave starts here, move towards the free end, and it's just like wrapping your rope with a little ring, right? A little ring that can displace up and down, like in a pole. And then what happens? The wave doesn't change phase upon reflection. See that? It's incident upright and it's reflected upright as well. That's what happens. And then you have the other two cases. Transmission, reflection and transmission of waves. From, let's see, I inverted the order, right? From a lighter string to a heavier string. Okay, let's do it. From a lighter string to a heavier string. Do you see? This string here is thinner than this other string here. Okay, so this string here is heavier than this other string. The density of this string here is heavy, is higher than the density of this other string, right? And then what's going to happen to our wave? It moves towards the heavier string, higher density string, and when it reflects upside down, changes its phase by 180 degrees. Okay. Can you remember that? That's easy to remember, right? It's kind of obvious. It's kind of makes sense, right? It's logical. Okay. And then we have a transmitted wave on the other side as well. Here you go. I'm gonna shorten this guy. And connect here. That's what actually happens in real life. Okay, let's play the movie. Here you go. Lighter string to heavier string, or let's say lower refractive index towards a higher refractive index. Okay, and then what happens when the wave is propagating in a heavier string towards a lower string? You know, there is no inversion on the phase of the wave. Okay. So now we can write it down. 4 important types of reflection. Reflection from a free end. The phase shift after reflection. After reflection, the phase of the wave shifts by 0 degrees. After reflection, the phase of the wave shifts by 180 degrees, right? Reflection from the interface between two media, from a heavy medium to a lighter one. Okay. Reflected wave shifts its phase by 180 degrees, and we have transmission of some of the wave towards the other medium as well. We have reflection and transmission. We have reflection and transmission, right? Here we have only reflection. Here we have only reflection in the first case as well. Here we have only reflection. Let's see. The other one, reflected wave shift its phase by 0 degrees. And we have some transmission of some of the wave towards the other medium as well. Similarly, we have reflection and transmission as well. Okay? 4 important types of reflection, wave reflection. 1042. Let's see, we can. Okay, so we covered what we covered so far. We covered the following. So far, we covered the following. 1, the principle of linear superposition, right? Wave equation. The wave equation. Okay? In general, the wave equation, which in general is written in the following functional format. I didn't write above, but I'm going to write here. The genetic functional format is like that. It's like the following. You know, function f, it's gotta be italicized. Yep. Okay. The functional format of a wave, the genetic functional format of a wave is this one here. Or we can even put a phase term in there. No, phase term is a constant, so, you know, plus and minus Vt, right? X plus and minus Vt. Plus and minus Vt. It can be, you know, sine of 2 pi over lambda x plus and minus Vt. Can be, you know, a linear function x plus and minus Vt. Can be a square wave that x minus plus and minus Vt, everything raised to the second power, and so on. Okay? The wave equation. Equation of a wave. What else? Superposition principle. Okay. Superposition principle. We see in the superposition principle, we have within the superposition principle, we have completely constructive interference, completely constructive interference, 2, completely destructive interference, and C, everything else in between, everything else in between. Okay? And what else? Reflection and reflection of a wave, reflection and transmission. and transmission of a wave, right? Okay. Reflection from a fixed end, reflection from a fixed end, no transmission. Reflection from a free end, no transmission. Reflection between a lighter reflection from a lighter medium, reflection of a wave from a lighter medium towards a heavier medium. Reflected wave is reflected wave has a phase shift of 180 degrees, and part of the wave is transmitted, right? Reflection of a wave from a heavier medium towards a lighter medium. Reflected wave has a phase shift of 0 degrees, and part of the wave is transmitted. That's what we covered. Okay, 3 different topics here. And you're going to need that to understand what's going to come next. Okay? So going back here. Yeah, what's going to come next? What I want to show you as well. Okay, we'll talk about that after the break. But first, let me take attendance. Today is the 2nd of June. Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Nestor Alvarado.
I'm here, Professor.
Okay. Monty Ambarchian. Are you there? Monte. Okay, I don't see. Oh, yeah, Monte is here, but it's not answering. So Isabella Ballesteros. I don't see Isabella here. Next is Justus Bowden. Justus, I see Justus here, but he's not answering my call. Next is Benjamin Carvajal. Thank you, Benjamin. Elizabeth Castellano. I don't see Elizabeth here. Next is Natalia Cordoba. I don't see Natalia. Next is Jacqueline Delgadillo. I don't see Jacqueline either. Jenny Diaz.
Here.
Thank you, Jenny. One more. Valerie Diaz. Valerie is here, right?
Here.
Okay, thank you. Next, Juan Escalera. Juan Escalera. I don't see Juan Escalera here. Oh, Juan is here, but it's not answering. Next, Bianca Eulocki. Bianca is here, but it's not answering. Next is Edwin Gonzalez.
Here.
Thank you. Eli Gonzalez.
Here, Professor.
Thank you. Manuel Hernandez Pineda. Manuel Hernandez. I don't see Manuel Hernandez here. Samantha Hubert. Thank you, Samantha. CJ Hutton. I don't see CJ. Amber Lopez. I don't see Amber. Next is Arely Lopez. Thank you, Arely. Genesis Lopez.
Here.
Genesis just joined us. Mary Michaelian.
Here.
Thank you. Galia Odabashan. Galia. Okay, I don't see Galia here. Ramon Olivares. No Ramon either. Taylor Forn.
I'm here.
Next is Jeremy Pittman. Okay, Jeremy. Okay, I don't see Jeremy. Let's see Monte. Conversion. Chico. Thank you, Monte. Stephanie Ramos.
I'm here.
Thank you. Leslie Rios. Thank you. Alexandra Romanov. Thank you, Alexandra. Jason Strait.
I'm here, Professor.
Okay, last but not least, Hema Torres.
I'm here.
Thank you. Let's see. Let's sum up how many students we have here. 18 plus those who didn't answer, right? No, 21. Okay. Juan Escalera, are you there? One more chance, right? Juan Escalera, Bianca Eulocki, are you there? And okay, thank you, Bianca. One more here, Justus. Okay, so let's have our break right now. Please, P07, go. Break. At 10:55 a.m. to 11:10 a.m. Okay? I will see you in 15 minutes. Stop sharing. Pause.
Deixar uma senha provisória para mim, porque agora meu marido está dando aula, ele não pode parar para colocar a senha aqui no computador.
Okay, I'm back here. Gente, o tempo passou rápido. Break. Let's take a look at the book, how we are here, how we are moving here. So here we go.
Okay, posso.
All the stuff that most of the things that I covered, right? It's not in the book. It's not in this chapter, right? Here is the principle of superposition that he deals just with, completely constructive interference and completely destructive interference.
No.
Then, like I said, that we have everything else in between. Okay, and now we are going to talk about Young double slit experiment. Like I said, is a classical experiment. Very important. Historically, it's very important. And just performed in 1801, in the first year of the 19th century, by Thomas Young. And this is a historic experiment, you can see here. And nowadays, we perform this experiment in all the time. Actual experiment, right? Not this one, but we cover here in this course. And it's a very simple treatment. It's not difficult. Mathematically, it's a very simple treatment to cover, okay? So how does it work? So let me start writing down the Tom Young's the double slit Young's experiment. Okay. Until 1801, it was thought that light behaved as a particle. Okay. Until Thomas Young proved otherwise. Light, in other words, depending on the conditions subjected to light, conditions that light are subjected to, comma, it may behave as a wave as well. Okay? And it's all dependent on the conditions, right? Okay? So recall that we studied geometrical optics, right? In the geometrical optics treatment, comma, light behaves as a particle. It travels in a straight line from one point to another, right? It travels in a straight line from one point to another. Thomas Young, unlike a wave, unlike a wave, it behaves as a particle. Unlike a wave, it travels in a straight line from one point to another. Thomas Young proved otherwise. It doesn't mean that geometrical optics, okay, this does not mean, doesn't mean that geometrical optics is incorrect. No, it doesn't mean that. This doesn't mean that geometrical optics is incorrect. No, it's not incorrect. It is correct. It is correct under certain conditions, okay? It's corrected and it's correct under certain conditions. That's the key way of describing it. Just like Newtonian mechanics works well for speed for particles. Traveling at a speed less than, let's say, 40% the speed of light, comma, geometrical optics works well when light interact with objects that are much larger than the wavelengths, than its wavelength, okay? So if light has a given wavelength and is interacting with an object that's much larger than the wavelength of the light, stick to geometrical optics. Geometrical optics works very well. It's a very simple treatment. Mathematically, it's very simple, okay? And that's the advantage of geometrical optics over wave optics. So, you know, there's no need to complicate mathematically your situation, okay? However, when the objects that light is interacting with start to become smaller and smaller, to the point that the object size is on the order of the wavelength of the light, then you need to consider the wave effects of light. That's how we decide when to use geometrical optics and when to use wave optics, okay? So here you go. Geometrical optics is a much simpler theory compared to wave optics. However, it fails under certain conditions. And the condition is whenever the object that is interacting with light has a size similar to light's wavelengths. Okay? And like I said, that's how Thomas Young. That's what Thomas Young proved. Okay, and let me give you an example. No, a picture, an actual picture of Thomas Young's experiment. "39. Let's see if I can find it here. Okay. Okay, here you go. I took a picture from an actual experiment. Okay. This is that what you see whenever you pass light through a double slit. And let me, here you go. Okay, so here you go. Here we have a double slit. Double slit right in here. Okay. So if you shine your laser monochromatic, preferably monochromatic, it doesn't have to be monochromatic, but preferably monochromatic. If you manage to illuminate, you know, this thing is just like an obstacle for light, okay? An obstacle for light that you drill a slit through it. Two slits. They're separated by a distance that's approximately the wavelength of the light. The wavelength of the light is around 600 nanometers. Okay, or let's say 1 micron. Suppose that you can create a slit like that, a double slit like that, with a separation of 1 microns distance, and then you shine this whole thing with your laser light. Something interesting is going to happen. Okay, when you project the image that goes through this double slit, when you project the image in a piece of paper, for instance, you get this pattern here. You don't get a single bright, you don't get two single bright spots, you get multiple bright spots. This type of behavior is typical of a wave, okay? If light were to behave just like a particle, right? You don't observe this many bright spots, you observe just two bright spots because you have two slits in there, okay? So when you illuminate, a double slit that are separated by a distance on the order of a wave of the wavelength of light, of the wavelengths of light, comma, instead of getting two bright spots on a screen, on a faraway screen, let's put it on a faraway screen, comma, instead you get multiple bright spots. Think about the guy first observing this thing, the situation. The first man to observe something like that. Okay, most likely it was Thomas Young. Most likely it was him. Let's take a look at Wikipedia. Double slit experiment. You know, we always find the double slit experiment. Wikipedia, double slit experiment. Let's see if anybody else preceded Thomas Young, right? Sometimes there are some people that managed to see that before Thomas Young, but he couldn't realize what was the explanation, okay? In modern physics, the double slit experiment demonstrates that light and matter can exhibit behavior as both classical particles and classical waves. This type of experiment, first performed by Thomas Young. It looks like he was the first one. In 1801, at the time when the British Empire was the most powerful one on the surface of the earth, right? At that time, the Americans were still getting their stuff together. And it was the superpower of the time, like the United Kingdom. And because it was the superpower of the time, they produced the brightest minds of the time as well. As a demonstration, here you go. That's where I got my illustration, okay? I got from Wikipedia. I'm not going, I should put it here. Credit Wikipedia. But we do have this equipment there at LA Harbor, and I show that I usually, I like to show that to my students. Unfortunately, I cannot do that here online, right? But that's what I mean. Oh, here you go. Double slit, right? A double slit here. Here you go. Here's a beam of light. Well, actually, they are illustrating that with electrons, but it can also be explained in terms of light as well. Instead of electron beam gun, I can write that down. See the thing here as being a laser source, laser pen. And here's the double slit. The laser light. Oh, what happened? I don't know what happened. Let's see. There seems to be a technical issue. We can retry if it persists. Okay, too bad. Okay, I cannot show that to you. I can only show this one here. Let's see if I can download it. Save image as. It doesn't let me save it. Yeah, it doesn't save it. But let's see, let's just repeat what I told you. Right here is a laser pen, right? Laser light comes from the laser pen and illuminates those two slits. The spot of the laser is large compared to the distance between the slit. Remember, spot of the laser is not the same as the wavelength of the laser, right? Not the same as wavelength of the laser. Okay, now he's finally saving here you go. Let's see if I can open it now. It's not the Zoom. Let's see if I can open it. Yeah, I can open, but it's terrible, huh? Man. Yeah. Okay, so this electron beam gun is replaced by your laser pen, right? And the laser is illuminating this double slit. The spot side of the laser is larger than the distance between the two slits. And then you have, at a distance, you have a screen in which you project an interference pattern that looks like just what you saw there, right? It looks like just this one too, same problem. Okay, that looks like just like that. Several bright spots. Okay. So let's take a look at Thomas Young. Thomas Young, personal life. He was born in 1773, died 1829, just 50, a little bit more than 50 years, right? Didn't live much long. 73, 23, 93, 50 something, 56 years. Wow. Yeah. He was a polymath, contribution in the fields of vision, light, solid mechanics, energy, physiology, even physiology, language, musical harmony, and Egyptology. Yeah, this guy helped Francois Champollion translate the Rosetta Stone for those archaeological nerds, right, of the class. I was watching YouTube a very nice story about the translation of the Egyptian hieroglyphs, okay? And the woman who was talking about that mentioned Thomas Young. And yes, he contributed to Egyptology. He tried to translate the Rosetta Stone, but didn't manage to do that. And the guy that really ended up translating it completely was Francois Champollion, a French guy. Okay, but let's concentrate on the double slit experiment, right? Last man who knew everything, it's described as the last man who knew everything. So Thomas Young didn't manage to translate the hieroglyphs because, he was doing that for fun only, right? He was actually a scientist, physical scientist. Here you go, personal life. I want to go there to religious views, wave theory of light, okay? In Young's own judgment of his many achievements, the most important was establish the wave theory of light, set out by Christian Huygens, okay? Christian Huygens, who came up with the actual idea of the wave theory of light, but he didn't have experimental evidence, clear experimental evidence. Christian Huygens was also the guy who invented the pendulum clock. Okay, wave theory of light. Let's take a look. Wave theory of light, principle, but it doesn't have unfortunately, they don't have the history behind it. Yeah, physical optics. Yeah, wave theory of light is connected with physical optics. Or wave optics, the branch of optics that interference, diffraction, polarization, and other phenomena, geometrical. Okay, other phenomena for which the ray approximation of geometric optics is not valid. Geometric optics is an approximation to wave optics. Okay. Yeah, they don't have much of a good article here on physical optics, unfortunately. But everything started with Christian Huygens, right? To do so, he had to overcome the century-old view expressed in the venerable Newton's optics that light is a particle, okay? That's one of the most difficult things to do in science, is to convince your peers that established knowledge is incorrect. Einstein had to do that. Thomas Young has to do that. And many others have to do that. People were leaning on the Newton's treatise on optics. And it's very difficult. When you have something like that, it's very difficult to try to change the minds of your peers, just like the theory of the ether that we had at the turn of the 19th to the 20th century, right? Physicists thought that it was necessary to have a medium in space for light to propagate. And it took years for scientists to be convinced that there was no need to have this fantastic medium for light to propagate. Okay. Nevertheless, in the 19th century, Young put forth a number of theoretical reasons supporting the wave theory of light, and he developed two enduring demonstrations. The important is the demonstrations, the practical demonstration, the experimental demonstration. That's why we remember him, right? To support this viewpoint. With the ripple tank, he demonstrated the idea of interference in the context of waters. Okay, that's the type of thing that we can do anywhere. Okay, just in your bath tube, you can do that. Can fill up the bath tube with water and then pluck your hand on the surface of the water. You're going to see waves propagating, right? And then if you pluck two of your fingers in the water, you're going to see water interference. You're going to see water interference due to the wave nature of the water wave. With the ripple tank, he demonstrated the idea of interference in the context of water waves. With Young's interference experiment, the predecessor of the double slit experiment, he demonstrated interference in the context of light wave. Let's take a look at Young's interference experiment. Okay, here you go. We have details of the Young interference experiment here. Isn't that nice that we have Wikipedia nowadays? Right? I didn't have that during my time. And we are going to go through this theory right now, but I want you to have a historical background of how the thing came about. Okay? This Young interference experiment today is used to explain the interference of electrons as well. That's how important it is, okay? Even today, 200 years later, we're still using this theoretical frame that was proposed by Thomas Young himself. Young, speaking on November 24, 1803, to the Royal Society of London, began his now classical description of the historical experiment. The experiments I am about to relate may be repeated with great ease. Very important. Repetitivity. Okay, if Thomas Young had done the experiment and someone else independent of him were not able to repeat his experiment, we wouldn't be talking about his contributions today. Okay, and very important, may be repeated with great ease. Okay, and it is at this point that people keep on asking, if it can be repeated with great ease, how come nobody else have been made to show this experiment before, or have been able to demonstrate this experiment before? Okay, hopefully, you folks are going to go through that in your future. Okay, whenever you go through that in the future, just be prepared. Okay, just be prepared for something like that. Discover something important that's so easy to perform, and yet nobody has ever been able to observe. Okay, whenever the sun shines, and without any other apparatus, then is at hand to everyone. Okay, the experiment I'm about to relate may be repeated with great ease. Whenever the sun shines, use the sun as a light source, not a laser, and without any other apparatus then is at hand to everyone. In the subsequent paper titled Experiment and Calculation Relative to Physical Optics, Young describes an experiment in which he placed a card, okay, measuring approximately 0.85 millimeters. 0.85 millimeters is on the order of 850 microns. Okay, notice that he did not use a slit, because we didn't have technology at that time to do the experiment with a slit, okay? Instead, he used a cards that were very thin, and they could behave like a double slit, okay? In a beam of light from a single opening in a window, and observe the fringes of colors in the shadow and to the sides of the card. He observed that placing another card in front or behind the narrow strip so that to prevent the light beam from striking one of the edges caused by the fringe to disappear. This supports the contention that light is composed of waves, okay? So that was the imagination that he used. How you're going to do an experiment that today we can look at very easily because we have technology to do that, right? How he could have done the double slit experiment if you couldn't had if you didn't have technology to produce a double slit at a very small distance. Well, he exercised his creativity and he used a card. Think about that. And a card behaves just like a slit, a double slit. Okay, the region at the top of the card is one slit. The other region at the bottom of the card is the other slit. That's how he could visualize something for his time at his time. Okay, so that's enough, right? Sometimes I get excited about those contributions, but what I'm going to draw here for you how Thomas Young actually did this experiment. He didn't use a slit, right? Like I mentioned. Let me zoom out. He used a card. Consider that a card, a very short card, a very thin card. Okay. I'm going to remove my slit here. And then he shone the light like that. Here you go. Here's the beam of light incident in the card. I'm gonna make my card a little bit thicker. Okay, here you go. And the card was very thin. There was technology to make very thin cards at the time, 850 microns, right? On the order of wavelengths. And he could see that there was some interference patterns. Card used by Thomas Young. Double slit experiment. Okay. Card used by Young. The card behaves as a two-slit device. Above the card is one slit. Below the card is the second slit. And the separation between those two slits is the thickness of the card. Okay? Twice. Now, so how can we treat this type of experiment, right? Mathematically, you can treat it very easily. No, but you need to convince yourself, okay, that this thing works. Too much, right? Too much. Let's see if I can simplify this drawing. Okay, I am going copy and paste it. I will start copy and paste again. I want more. I'm gonna get rid of everything here that you see. Okay. Here we have the screen on the right. Okay. And on the left, we have the double slit. The slits are separated by a distance d, and the screen, it is a position that's very far away from this slit. It's not in scale, okay? What you see here is not in scale. Let's make sure ruler grid lines. Yeah, looks like everything is okay. It's just this line that's not. The distance to the screen is much larger than the distance between the slits. Okay, now, so we have a light beam that's incident on the left side. I'm gonna draw this light beam as a, let's see here. Let's see if I can draw it as a, I'm not finding what I want here, unfortunately. Huh. Oh, here you go. Here you go. I'm gonna draw my light beam as a, something like that. Okay, oops. And I'm gonna send to the back. Okay, so light beam from the laser. Can you picture that? What's going on here? Huh, strange. Let's see, I'm going to no fill, okay? My light beam is a cylindrical in nature, right? Geometrically cylindrical. And then after being incident on this slit, we are going to have one light ray propagating from the top slit, right? Can you see that? And another light ray propagating from the bottom slit, from the lower slit. And those two light rays, they are going to meet at this point here in the screen. Not just at this point, but at several points along this screen. Okay? And at each point in this screen, we are going to form an interference pattern. So you can imagine a sine wave propagating from the bottom slit to the point P, and another sine wave propagating from the upper slit to point P as well. And at this point P, there will be interference between those two separate waves. Okay, and I'm going to, cylindrical beam of light. I'm going to write that down here. Cylindrical beam of light, like that. Can be your laser beam, your laser pen, cylindrical beam of light, illuminating the two slits simultaneously. The beam of light has, from a laser has a size, right? And now I can, here you go, name it here, name it there, right? And now I'm going to do the actual calculation. And now in the next slide, I'm going to remove this thing, this beam of light here, so we do not have too much stuff to deal with, right? So here you go. What we have here in this drawing, we are going to have an horizontal line. Okay. That is our reference. We're gonna have a horizontal line here. But first, wait a minute, before we introduce this horizontal line, let's introduce the other one. Here you go, this one that passes through the middle of this slit is better, right? That would be our reference. Let's make sure that this line is horizontal. Yep, this line is horizontal according to my grid line here, yes. And the mid of the slit is my reference, okay? Going all the way up to the point P, and we have an angle theta here. We can do the same for the other two lines. Okay, we can get a horizontal line starting at the lower slit, and we take this horizontal line as a reference to measure the angle. What I'm telling you here is that this angle here, strictly speaking, this angle here is theta plus something else, okay? Plus something else. Let's see. Strictly speaking, but the truth is that this something else is very small. It's very small. It's so small. Okay, it's so small. Why is it so small? Why is this small? It's small because the distance of the screen to the slit is very large compared to this distance here, right? If we look right now, it doesn't look small because the drawing is not in scale. But if you put it in scale, you're going to see the further away this screen is, the closer those lines becomes to a parallel line, okay? So I can go ahead and say that it is approximately theta, almost the same angle theta. Because L is much greater than D, we can say that this angle here is approximately this angle here. Okay, but let's say I'm gonna put it equal for now, okay? Minus F, minus, let's see, I'm gonna put a delta theta, okay? Symbol, let's see if it, for some reason it's not changing. Why is that? Ay, 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 ay. It's not changing to symbol for some reason. Let's see what's going on here. I'm gonna copy this one. Okay, this one is working. Yeah, for some reason this one is working. Okay. Theta plus delta theta, okay? Oh, equal lowercase theta. Yeah, here you go. Now I can substitute that. Strictly speaking, like I said, right? Strictly speaking, this thing is gonna be theta plus delta theta. And I'm gonna make it in red color. So it is associated with the red line. And we repeat the same for the light, for the line, for the upper light wave, right? But instead of theta plus delta theta, we are going to have theta minus delta theta. And the line here is going to be a blue line. Blue color. This line is going to be blue. And this angle here is going to be blue as well. Like that. right? Strictly speaking, this one is the theta plus delta theta, and this other one is theta minus delta theta. But because this distance here is so large, we can neglect this term here, okay? We can write that down as being approximately theta for both of them. Like that, approximately theta. That's our first approximation. We need this approximation to get a simple relation, okay? We need this approximation to get a simple relation. And now I can start adding other stuff too, right? And that's what I did here. Make sure that the drawing doesn't become too crowded. We're increasing the crowdedness of the drawing by making one slide after another one, right? So here you go. I'm gonna call this one D1. This one here is gonna be D1, but it has to be a red color. The difference in the phase is going to be proportional to the difference between those two path lengths, okay? The difference in phase is going to be proportional. One full wavelength is equal to 2 pi to 200 to 360 degrees phase difference, which is 0 degrees. Make sense? Okay? So why did I put that? The D1 and D2, let's see. Okay, I'll get there. I'll get there. And now I'm gonna show you something else. Copy and paste. I am going to come up with a right angle triangle. Here you go, a right angle triangle right in here. Here's my right angle triangle, right? Here's my right angle triangle. And let's see. And now what I'm going to do, I'm gonna say that this length that you see right in here between this lower slit and the point of intersection of my right angle triangle is very small compared to the length of this guy. Okay, it's very small compared to the length of this guy. And because of that, we can state that this distance that you see right in here is approximately the other distance D2 that you saw there. Okay, and let me change the color, the blue color. Again, this is an approximation, but it's an approximation that works very well. Okay, this distance is D1, and this distance, I'm not saying that it is D2. No, I'm not saying. I'm saying that it's approximately equal to D2, and I'm gonna put in a different color. Let's put it in the green color because those are different quantities, right? It's not exactly D2, but it is D2. Step by step, right? If this one from here to here is D1, this one is D2. Let's see. And by the way, I have to do something else here too. Yeah, I gotta come up with this one here. Okay? This line here is parallel to this other line. Okay? If this one is D1, this one is approximately D2, it means that this little distance that you see right in here is approximately the phase difference. Is approximately D1 minus D2, okay? And I'm going to illustrate that. Sometimes those drawings become very complex, right? Here you go. What did I do here? Let's see what I did here. I was supposed to do it here, right? Yeah, here, that I was supposed to do. Okay. Here is the phase difference. Not the phase difference, but is related to this phase difference. Is the optical path length difference between one light ray and the other light ray. Okay. You can do those drawings there at home. It's not difficult. This thing is just like, this guy is not supposed to be here. Let's see. Let me erase it, erase it, erase it, erase it. Yeah, here you go. I erased everything. Don't need to erase anymore. Okay. And now that we have this triangle, right? We can come up with our simple approximation that we already made an approximation, right? Well, the approximation that we made is that those two light ray paths, they are almost parallel to each other. Okay? Referring to the drawings of the class, you know what? I'm going to copy that and paste in my snipping tool. Yeah, I'm going to copy that. Okay, interference. Okay, here you go. Consider, you know what? I'm gonna come up with a simpler one. Okay, this one here. This one here. Yeah, here you go. It's not good to. Here you go. I'm gonna use this one here, this illustration instead. Consider the above illustration. Right? Consider the above illustration. A laser beam illuminates a double slit from the left. And this beam is broken down into two separate light rays. One red, one illustrated as being red, illustrated in red color, and the other in blue color, okay? In blue color. Okay, because L is much greater than D, the separation of the slits, comma, these two lines are almost parallel to each other. Okay? almost parallel to each other. Because of that, we can state that both rays, red and blue, make an angle that is approximately theta with respect to the horizontal. Okay, with respect to the horizontal. So that's gonna be my next drawing that I'm gonna show to you. Go. That's the drawing. Copy. See below, right? See below. Almost parallel to each other. It doesn't look parallel because I didn't put the figure in scale. But if I stretch it as much as I can, those light rays are going to become more and more parallel to each other, okay? Let me show you. Let me give you an example. Stretching in the horizontal direction is the same as compressing in the vertical direction, okay? Look what happens to those blue and red lines. They look that they're becoming more and more parallel to each other, right? That's how we simulate, that's how we illustrate the fact that those light rays are almost parallel to each other. And now that their angle are almost the same, we can now state that there is a right angle triangle here that we can make to extract this right angle triangle here to get our equations. What time is that? 12:08. Let's go a little bit longer. Let's see. Let's see where's my right angle triangle. Right in here, my right angle triangle. It's right. Let's see. Let's see if I have a better. Oh, that's the one I want. That's the one I want. Let's move it up. Okay. Here's my right angle triangle. This right angle triangle is the same as this one. Remember that I told you that this small difference here is going to be approximately d1 minus d2. That's what I put it here, d1 minus d2. And let's not forget that this angle is also approximately theta, right? This angle is approximately theta. If this angle is approximately theta, this one must be also approximately theta. And how do I know that? Well, very simple. Let me draw another, not this one. Remember that the upper beam, right, is coming out here. Right? The lower beam is the side of the triangle here. The lower beam is almost parallel to the upper beam. Right? This angle here is 90 degrees. Right? This angle here must be 90 degrees because those two light beams are almost parallel to each other. And let's not forget that we still have the horizontal line here, okay, that we drew before. And this horizontal line makes an angle of almost theta. Almost theta, right? If here is 90 degrees, here is going to be 90 minus theta. Because this one is 90 degrees, this angle must be theta. Okay? So now we have my right angle triangle that will allow us to solve for the conditions of bright spot and dark spot. Okay, let's take a break now. Let's go 4 more minutes. Let's go another 4 more minutes, okay? And then we can remind me when it gets to 12:15. Let's go 4 more minutes. Now I can go to my I'm gonna copy this one as well, and I can go. Okay, go here. D1 minus D2. Okay, so here you go. D1 minus D2 divided by D. Don't forget this is a right angle triangle. Is going to be sine of theta. Okay? Copy. I'm going to put it right here. D1 minus D2. And I can say it's approximately equal to sine of theta. Let's be here. You go. Sine of theta. Oh, let's not forget there is also a D here, right? Here you go. Opposite side over the hypotenuse is sine of theta. Okay. But then, because this angle here is very small, it's very small, but theta is also a very small angle. But theta is also a very small angle, a very small angle. Okay, so let's keep track of every first approximation. First approximation. Okay, first approximation. One. Lower and upper light rays are almost parallel to each other. This approximation implies that what this approximation implies? The approximation implies that theta 1 is approximately equal to theta 2, which is approximately equal to theta. Okay? Theta 1 and theta 2 is the angles here at the lower and upper. And I can even, let's do that. Let's see, 12, 15. Okay, that's the first approximation. Very soon, when you come back, I'm going to introduce you the second approximation, okay? So break from 12:15 p.m. to 12:30 p.m. Okay, I see you in 15 minutes. Okay, I'm back here. Can you see the screen? Am I sharing my screen, by the way? Let's make sure I'm sharing the right screen. Okay, here you go. First approximation, let me correct what I said there. The first approximation is the following. First approximation is L much greater than D. That's the first approximation, okay? When I say much greater than D, what do I mean? I mean that L must be greater than 10 times D. That's a good parameter. That's a good rule of thumb, okay? And that holds. That holds very nicely because D usually is less, the separation between slits, right? D, the separation between slits, D, the separation between slits, D is usually less than 1 millimeter, less than 1 millimeter. And the distance to the screen, when we perform those experiments in the classroom, the distance to the screen is at least 1 meter distance, 1 meter of distance. And we are talking about, or 1,000 times D, okay? That's what we usually doing. So this approximation holds very well experimentally. So this, as you can see, this approximation holds very well in the experimental setup, in real life, right? In real life. Okay? Now, L much greater than D implies that the lower and upper light rays are almost parallel to each other. Okay? It's still just the first approximation. I didn't introduce a second approximation yet. Okay? This approximation also implies, okay? This approximation also implies that the angle that the lower light ray makes with the horizontal is going to be approximately equal to the lower to the angle that the upper light ray makes with the horizontal, which is approximately theta. Theta is the angle that the middle point from the slit to the screen, right? That's the first approximation. Okay? Then, and according to this approximation, where is that? Someone is trying to come in. According to this approximation, we have the following relation. Okay? That's my first approximation. Now I'm going to introduce a second approximation. Now I'm going to introduce a second approximation. Let's keep track of all the approximations, okay? So we don't lose track of them. And we are convinced that they work well. Now I'm going to introduce a second approximation. The second approximation is the angle theta is a small angle, And by a small angle, I mean at most 40 degrees. At most 40 degrees, okay? That's what I mean by small. When we have a small angle approximation, what we can use an approximation under the circumstance, okay? Under the circumstance, the sine of theta is approximately theta, okay? And I can prove that to you using a spreadsheet. I can just prove that to you, but don't forget theta must be written down in radians, okay? Let me prove that for you, okay? Here you go. Theta, I gotta do that in degrees. Theta in radians. And then I'm gonna do sine of theta, okay? And I'm going to start at 0. Every half degree, I'm gonna increase the angle by every half degree. And you're going to see that there is. And I'm gonna go all the way up to, let's say, 40 degrees, 45. And you're going to see 50 degrees. Here you go, that's enough. Theta in radians, I gotta change that to radians. 0 degrees is 0 radians. Half degree is 0.0087 radians, and so on, right? I'm gonna leave that for now. And now I'm going to write down the sine of theta. And then I'm going to show you the percentage difference. Okay, percentage difference between sine of theta and theta in radians. Multiplied by 100 divided by the exact value.
Ah, ok, obrigada.
Okay?
Obrigada, hein, João.
You know,
Não, tchau, tchau.
sine of theta is 0, radians, the theta in radians is 0, consequently the percentage difference is 0, okay? So here you go. Look what happened. When it's half degree, the percentage of difference is 0.001%. It's almost nothing, right? Let's say at 10 degrees. At 10 degrees, what's the percentage difference? At 10 degrees, the percentage difference is less than 1%. It's 0.5%. Okay? And keep on increasing. Let's see, 20 degrees. 20 degrees, you have only 2% difference between sine of theta and theta. Okay? And let's keep on increasing. And let's see at 40 degrees. How much percent difference does it go? Okay, that's when it starts to increase. We already have an 8%. It's not 10% yet. I have told you, right? Anything less than 10% is a good is a percentage difference of 10% is good enough. Okay, so you can go up way up to 45 degrees, and still this approximation is still gonna hold very well. Okay. So I proved to you that if small angles for us can be all the way up to 40 degrees. But if you want to be conservative, you can restrict your measurements all the way up at most 30 degrees. Okay? So that's the approximation that we have. And now that we have the second approximation, all right? Here you go. We have that here. That's the second approximation. Okay, well, okay, so we have only 2 approximations. Okay? L much greater than D, and we are restricting ourselves to very small angles from the normal of the slit. If you want to see that right in here you go. The angle that we are talking about is this angle here, okay? Is this angle here. That's the angle. And, you know, if you restrict that between within 20 degrees, that approximation, that formula, the approximated formula holds very well. And now what are we going to do? We got the optical path length difference between these 2 light rays, okay? What you're going to do next, now we are going to predict where the bright spots of the double slit experiment occur. The bright spots occur, okay? The bright spots, bright spots occur whenever the phase difference between the two light rays are equal to 0, 360 degrees, 720 degrees, etc. Okay? Or n times 360 degrees. Okay? That's when we have the bright spots, 700 degrees, etc. Or, for n equal to 0, 1, 2, 3, 4, ba, ba, ba. Okay? When you have this difference in degrees, or should be, which, by the way, right, is equal to n times 2 pi radians, right? Don't forget, put that in radians symbol. Good. Okay. So whenever D1 minus D2 is proportional to this phase difference, okay, we're going to get bright spots. And just going back right in here. Okay, the brightest spot that we have, the central spot, is going to be this one here in this 1, 2, 3, right? 1, 2, 3. Yeah, the central spot is going to be this one here. This central spot is located at 0 degrees. Okay? And this one is located at certain degrees, another degree higher, blah, blah, blah. Okay? But, how do you translate the optical path lengths in terms of the phase? That's the question that you have to ask, okay? The next question is, how do you translate the path difference in terms of the phase angle? Okay? Okay, the way you translate it in terms of the phase angle is in terms of the wavelength. Okay? When it goes like that. The way you do that is in terms of the wavelengths of the light. Whenever the path length difference is equal to a multiple integer of a wavelength, then we have constructive interference, right? Just go back to that initial drawing that I showed to you, right? So here you go. Let's see. Not the initial drawing, but go back to that simulation that I showed to you, right? Here you go. When the phase difference is equal to 0, right? What does it mean? It means that one wave coincides with the other wave, okay? If I go ahead and put a 2 pi difference here you go, 2 pi difference here, we're going to see that those two waves are again in phase. So I'm going to plot them separately. Yeah, let's plot them separately so you can see. No, that's not the other one. I want the other one. I want this one, insert, and I want the other one. insert. Where is that? Okay, here you go. See, they are in phase. Okay, when they are in phase, you have constructive interference. And in order to have those two in phase, the difference between the phases must be a multiple of 360 degrees. Okay? And the way you do that is in terms of, okay, so here you go. The wave equal to the integer of a wavelength. Okay, so here you go. Whenever D1 minus D2 is equal to a multiple number of wavelengths, remember that? Okay. Then, whenever we have constructive interference, in this case here, n is an integer number equal to 0, plus and minus 1, plus and minus 2, plus and minus 3, etc. Okay? So we have destructive interference. We have destructive interference whenever completely, let's put, we have completely destructive interference, we have completely constructive, let's put it this way, right? Make it very clear, completely constructive interference. 3 minutes for the class to end. Let's see if I can do it. We have completely destructive interference whenever, the path length difference is equal to a half of a wavelength. And we gotta put like, here you go, 1/2. Okay? And put the parentheses here. Here you go. N equal to 0, plus or minus 1, plus or minus 2, etc. It's not M here, right? Let's remove this M from here. It's actually, etc. And then you have everything else in between, all right? So now we can write that down. We can find out, that we are going to have, so we have constructive interference for the following theta angles. Here you go. D theta equal to n lambda. And this theory holds very well, folks. You'll be amazed at how well it holds experimentally. I have done this experiment several times, and we always get a very good correlation, okay? So here you go. Constructive interference and theta max. I'm gonna put it theta max. Oh no. I gotta trick this guy into believing that I'm not writing max, okay? We have theta max whenever n lambda over d, n is the integer number. We have destructive interference, 1250, 1, 2, 3. Destructive interference whenever for the following theta angles. And here you go. Replace n with n plus half. Okay? Mean. And then I'm gonna replace right in here, replace right in here. Okay, and when we match this theory with the actual experimental evidence, we get like a perfect fit. Okay, So it's 12:50 right now. So far I covered only 27.1 and 27.2. So let's see if we can cover 27.3 on Wednesday, okay? So I see you the day after tomorrow.
Thank
Thank
you,
you.
Professor. Bye.
Welcome. Bye-bye. Hello, Justus, are you there? Eu te devo. Quanto eu te devo? Eu te devo?
Então sei nesse caso mesmo, porque no artigo tem a saída dele, a entrada lá para o subterrâneo é um tubo de PVC, né? Mas o PVC ele é isolamento, ele é um isolante térmico. Né? E a gente tem que pensar também que provavelmente isso daí vai condensar e vai gerar água lá dentro. Então a gente precisa ter um sistema para poder retirar essa água lá. E algo que seja automático, né? Tem que pensar nessa situação também, porque vai ter condensação. Provavelmente vai ter água nesse sistema e a gente vai precisar eliminar.
Hello, can you hear me?
There you go. I can hear you. Can you hear me, Professor?
Yeah. Alright.
Sorry, I was supposed to come in last Wednesday, but I didn't realize I had a final that same day, so it's
Yeah.
taking a little longer than I thought. But I just wanted to check in to end of semester. I've been studying. I'm ready. I think I'm mostly ready for the exam tomorrow, but I'm doing the homeworks online just to keep reviewing.
Okay. What about Jasmine? Do you need help, Jasmine?
Hi, how are you?
Okay, that's okay. Okay.
I'm doing good too.